Hello, welcome back. And for this lecture, we will be moving on to a next topic, which is called relative extrema. Relative extrema, right? Or local extreme, right? So this is for plural or maximum or minimum. Okay, so let's say a graph such as this. Okay, something like that, where these points, right, the low highest and the lowest point, right? So these are local or relative max, right, or local max, yeah. So these are the points. So these are the points, yeah. And these points are the local minimum, yeah. Okay. So for example, right, so it's actually a build up from what we have learned in the earlier of this chapter, right? So we are through all that knowledge that we have learned, like the finding the decreasing interval, increasing interval, concave up, concave down, inflection point. These can help us find the rel rel relative extrema. Okay, so given y equals to x e to the x square, right? So we know that through, this is from the previous lecture where we know that inflection point, inflection at x equals 0, right? So what else? Also that we know that function is always increasing, right? Since the derivative of it is let's see if I can take you back to that. If where was it? Yep, this portion, right? The last part that we did. So where the increase decrease part, we say that e to the x square is always positive, right? Then therefore our graph, our function is always increasing. Yeah, okay. And based on the concavity here, we say that concave up uh, after 0, and then concave down before 0, and then inflection point at x equals 0. Okay, so let's go back to this. Okay, see, so 0 here, we say that this was a concave down and concave up. Okay, so back to relative extrema. Okay, so definition, a function as a relative maximum, or we can say that this is a local max, right, at x naught if f of x naught is greater than f of x for all x in an open interval. Okay, and then that's this first one, and then the second one is that a function has a relative minimum, so-called local min at x naught if f of x naught is lesser or equal to f of x for all x in an open interval containing x naught. Right? So, oh, here is supposed to be greater than or equal to, right? So it's not just greater than, okay? Let's see, what else? Okay, let's move on. That's the definition. Okay, so we say that x values where relative max or min occur are called critical points. So basically, I think I kind of mentioned it before, uh, maybe in the last lecture, I believe. Its derivative will be 0 or doesn't exist. Okay. So theorem, suppose that f is a function defined on an open interval containing x naught if f has a relative uh, extrema extremum at x equals to x naught. Then x equal x naught is a critical point. Okay, so x equals x naught is a critical point of f, so that is f prime of x equals 0, or f prime of x does not exist. Okay, that's 0. Okay, let's try. Let's try some. So we say f prime of, let's say that given f prime of x equals to 2x over x minus 1, right? So so in that case, right, so what make it 0, right? So then 0 will make it 0, right? And then the other one is that x cannot be 1, right? Because of the denominator that gets to 0. Okay. Okay, so that's 2. And then so let's see. So something that you have to be careful. Oh, sorry, it's not cafe, but careful. Okay, is that let's say given x cubed as our function, x y, and then f of x. So let's say that we have f of x equals x cubed. Okay. So critical points, right? So we say f prime of x equals to 3x squared, right? Then we set 3x squared equals to 0, and x is equal to 0, right? Then in this case here, even though we get to the point where x equals 0, right? But in this case here, it is not a relative max or min, right? Because at 0, right, at x equals 0, this part here is not the highest nor the lowest point within the graph. So that's something that you have to be careful with. So that's where our previous what we learned in the previous lecture comes into play, right? So that's where we want to find out which are the critical points and which are not the critical points. Okay, so that's and let's say we another example is that we have something like this, right, as a function x and y. And in this case, let's say that we have a point here where it is a vertical vertical tangent line. Then in that case, we will not we will also not have a relative max or mean, right? So that's something that we have to be careful with. Okay, now one we say fine. So this is an example. So fine critical points plus identify critical points. Sorry, I think I forgot one word. So it's the identify which critical points are stationary. Okay. Okay. So what we do is that, okay, here's the given function. So let's say f of x equals to 3x squared minus 4x plus 2, right? So we derive it. So we get 6x minus 4, and then we set that equal to 0, right? So then 6x minus 4 equals 0. Then we end up getting x equals to 4 over 6, which is going to be 2 over 3. So what this is that the this is our stationary. Okay. Okay. Now that's just a quick example how to find critical points. Okay. So 2 f of x equals to x squared x minus 1 2 over 3. Okay, so we derive it using product rule. Okay, so then we get 2x, and then the second one stays 2 over 3 plus x squared, and then 2 over 3 comes down, parenthesis x minus 1 to the negative 1/3, right? Minus 1 on the power, and then multiply by 1 because of the derivative of x minus 1 is 1. So let's see. Yeah, I'll leave that as it is. So this stays the same, 2 over 3 plus, and then this part here, I'm gonna change it to 2x squared over 3 x minus 1 to the 1/3. Okay, now once we get that, let's see what I want to do. Okay, I want to find I want to get the common denominator so that I can combine those two together, right? So then I'll multiply top and bottom for the first one with so what I do is that I multiply 3x minus 1 to the 1/3 top and bottom for the first part. And then that multiplied by 2x x minus 1 2/3, right? Plus the same thing. Okay, and we distribute it, so then we get 6x on top. And because I decided to multiply these two together, right, then the power add, right? So then it multiply become x minus 1 to the power of 1, right? 1/3 plus 2/3 becomes just 1, right? So and then this is all over the same thing, which is 3 times parenthesis of x minus 1 to the 1/3, right? And then plus the same thing, right? Now we can add them together, right? First we have to distribute the 6x, right? So it becomes 6x squared minus 6x plus 2x squared all over 3 times x minus 1 to 1/3. Okay. And then combine like terms again, we get 8x squared minus 6x all divided by 3 times x minus 1 to the 1/3. Okay, I know it's a lot of work. Okay, so that's the derivative. So this is f prime, right? So once we get that, right, we want to set it equal 0, which in this case, so we want to set it equal 0, right? Then therefore, 8x squared minus 6x has to be equal 0, right? So factor out the x. Well, I can factor out both 2 and x, right? So then we left with 4x minus 3 equals 0. Then we get 2x equals 0, which leads to x equals 0. And then we have a 4x minus 3 equals 0. Then x will equal to 3 over 4. Okay. Then in these two cases, these two are stationary. Okay. And note that f prime of x does not exist at x equal 1, right? Because the bottom part here, what makes it 0 is that 1, right? So if we replace 1 with the x, then the bottom becomes 0. So therefore, f of x does not exist when x equal 1. Okay. Okay, so I think I would stop here. And then in the next lecture, we will dive deeper into this. Okay, and I'll see you in the next one.